Welcome back to the AI Research Roundup. I'm your host, Alex. Today is May 6, 2025. We're diving into an ICLR conference paper titled Scaling and Evaluating Sparse Autoencoders, published about 3.5 months ago on January 22nd, 2025. This paper tackles how to effectively scale and assess sparse autoencoders, or SAEs. These are models designed to extract interpretable features from language model activations, and this work focuses on improving how we train really large ones. Alright, so this first figure really visualizes their findings on scaling laws for what they call top K autoencoders. These directly control sparsity by picking the top K active features, or quote-unquote latents. The left plot shows reconstruction error, that's mean squared error, or MSE, decreasing as compute measured in flops increases. The right plot then shows MSE scaling predictably with both total latents and that sparsity value quote-A. This predictability is key. Building on that, this next figure compares their top K approach to other activation functions. On the left, with a fixed number of latents, top K shows a better trade-off between reconstruction error, that's the mean squared error, or MSE, and sparsity, which is the L0 norm, or count of active features. Then on the right, at a fixed sparsity, top K's scaling with the number of latents is steeper, meaning its performance improves more rapidly. Okay, so now we see how the size of the underlying language model, what they call the subject model, impacts things. This plot shows normalized mean squared error, or MSE, against the number of latents for different subject models from the GPT-4 family. The key takeaway is that larger subject models, indicated by more pre-training compute, need more latents in the autoencoder to reach a similar reconstruction error. This really underscores the scaling challenge. Alright, so building on the need for more latents, this figure shows how the learning rate interacts with the number of those latents. We're looking at normalized MSE versus learning rate, with each colored line representing a different autoencoder size. The numbers like 7.9b above the points show tokens to convergence. It's about optimizing the learning rate for different scales to train these sparse autoencoders efficiently and get good reconstruction. Well, moving beyond reconstruction, this figure evaluates feature quality by comparing top K to other activations using quote downstream loss. This essentially measures how the autoencoder's features impact the language model's actual predictions. Lower is better. On the left, with a fixed number of latents, top K shows a superior trade-off between this downstream loss and L0 sparsity. And on the right, at fixed sparsity, top K gives lower downstream loss for a given reconstruction quality. So shifting gears slightly, this figure presents two heat maps for more feature quality metrics. Probe loss on the left, and logit diff sparsity on the right. Probe loss tests how well the autoencoder can recover specific, hypothesized features. The heat maps show that generally, having more total latents, that's N, improves both metrics, indicated by the yellow regions, though things get worse if the features become too dense, like at L0 equals 512. So to wrap things up, the big takeaway is that this methodology allows for reliably training extremely large sparse autoencoders, or SAEs. And crucially, scaling these SAEs, which use top K activation to directly control sparsity, or L0, really improves reconstruction, that's mean squared error, or MSE, and the quality of the extracted features, or latents. Thanks for tuning into AI Research Roundup. I'm Alex.